Hi, so today I've got this toothbrush, a Sonicare Philips Sonicare toothbrush on my bench with a little extension, what you can see over here. So that's an A.C E eeprom, which usually sits on the board in a much smaller package. I just glued the bigger package onto the PCB to have easier access to the pins. And what this toothbrush does is it actually turns on the LEDs, as you can see here. There we go. But there's hardly any vibration on the shaft. Just a high-pitched sound from the motor is noticeable. But what it does is it is able to indicate via the 30 seconds timer that you should change the sector of your mouth while brushing. Come on, you can do it. There we go. So, so that tells me the basic circuit is working. There's just another problem here, which we might solve in the next few minutes. I will show you a bit of a deep dive into the contents of the eeprom and hopefully fix that problem, which your toothbrush might have as well. Otherwise you wouldn't have found this video. So let's get into it. And the model I'm talking about is just a standard sonicare toothbrush. And I'm not going to show you how to open up the case. There are lots of videos on YouTube where you can find information about how to open the case without any damage. So that's not the subject over here. I have the electronics on my bench here right now, and I hooked up an Arduino Due in parallel to the eeprom, which is still part of the circuit of the brush's board. Here you can see the schematics how I hooked that up. And with my Arduino I can now change certain values in the A.C.E eeprom and find out what the toothbrush thinks about that and how it behaves if you change those values. So the general problem with this brush is that it has water damage. So this seal over here is broken, and water gets into the case and damages the electronics. And before I started deep diving into the circuit board, my suggestion was that they at Philips actually store the resonant frequency of the mechanics somewhere in the eeprom or in the microcontroller. For that, and the purpose is that the mechanics, like the brush, which actually vibrates the brush head, has a certain resonant frequency, and the closer you get to this resonant frequency, the more optimal is the operation of the brush. So for every brush they measure this mechanics over here and the resonant frequency and store it somewhere in the brush. And due to some reasons which nobody actually knows why, the brush maybe stores a wrong value for the oscillation in the eeprom, or it just loses its configuration, and then you end up with a brush which falls back to a default state, and that default state has a frequency which actually doesn't fit the mechanics. Yeah, and therefore you hear a sound and the LEDs come on, but the brush actually shows no movement at the head. And that's what I'm going to show you now on the oscilloscope screen. There we go. You already see a picture taken from the brush, and that was the 30 seconds timer. What you can see here in white is a reference recording from a working brush, and here is the schematics of where that signal comes from. It's from one motor line measured to ground. Let me just turn off the second channel here. Oh, wrong button, sorry. There we go. So, and in yellow you see the same measurement on the brush which has a problem. And if you measure the reference frequency from the working brush, it turns out to be something around 300 and I don't know, 331 Hertz for one period of the motor oscillation. And if you compare that to the non-functional brush in yellow here, you can see that actually the frequency is much higher, obviously, and it turns out to be something around 1.9 kilohertz. So that's far too fast for actually moving the mechanics in the correct way. Alright, here you can see my serial monitor of my Arduino, and I've written a few lines of code which allows me to read the EEPROM contents, and that's what I'm going to do here. So there we go, that should give out the contents. It's a 1 kilobit I2C EEPROM, and that's all what's in there. And what I found out already is that here on addresses 02 and 03, that's the positions which have something to do with the frequency of the motor operation. And let me show you what happens when we erase the EEPROM completely. I've written some lines of code for that as well. That allows me to set it back to a state which it would have if it was a new EEPROM. So there we go, erase complete. If I read the contents again, you see every address contains FF. That's just, yeah, like I would have soldered a completely new EEPROM onto the PCB. That would be the same. And if I power cycle the brush now, it's connected to my laptop, to my power supply, laboratory power supply. If I power cycle the brush now, the controller occupies the data in clock lines for a few seconds, which you just have to wait until you can access the EEPROM. So let's try to read the contents. Now there you go, that's the effect I described before, lots of zeros, because the controller occupies the data lines for a short period of time. Then you can either measure to find out when the controller is ready, or you just try it a couple of times, like so. There you go. Now it worked out. And as you can see, there are values in the EEPROM which I definitely erased before the power cycle. And now if you power cycle the brush, there are default values in here. You can see there is 4E20 at 0203 once again, so that seems to be a default value which the brush writes into the EEPROM. And if you look over here, you can see the effect of those values. I turn the brush on, or at least I try to, and the lights come on, and you can hear, you can barely hear a sound from the motor, no vibration. You can turn on and off the brush, the lights come on, but nothing happens. And now I'll show you over here once again what I found out. So what we do now is I can change bytes single bytes in the EEPROM by entering a value, by entering an address first and the value afterwards. And at the address 02, let me look that up. Just because I tried this out before, so I have to look into my notes what to write at address 02, so that there is at least a result you can actually see. So what goes in there is 0A at address 02, and at address 03 there needs to be 39. So that's now written into the EEPROM. Let me show you this here. Make it a little bit clearer by clearing the output and read the contents again. There we go. So you can see now there is 0A and 39 at the addresses 02 and 03. So now we are going to have a look once again at the brush, what it does with these values in the EEPROM. So there is our little brushy. Bit more focused maybe. Let me show you once before what I mean by power cycling the brush. I've got it hooked up to this laboratory power supply here, and by power cycling I mean I turn the voltage off, and then wait a bit and turn it back on. So that's the same like you would remove the battery and put it back in. And as soon as you power cycle the brush, it starts to read the contents from the EEPROM once more. So now we've changed the two values, and let's see what happens now if we turn on the brush. There we go. You can clearly see or clearly hear there's the sound is quite a bit louder, and I mean that's a little bit wibbly wobbly here on my bench. If I try to fix it or hold it by hands, you can see it actually vibrates much stronger than before. And if we have a look at the oscilloscope once more, let me turn this on here. There we go, we got our reference, and if I turn on the brush, you can see it has a different frequency than before. Here's the screenshot from before with the default values in the EEPROM, and if we measure the new frequency, we can see it's much lower. It's about 262 Hertz right now. So that means the conclusion is you have two values in the EEPROM which you can use to modify the frequency for the motor oscillations. And the one on the address 02 is the coarse one, and for fine-tuning it's the address 03. So there we go, that's the main problem for this particular problem on this toothbrush. This content here, which I would like to call modified default content, that's what I would put down below in the description box, so that you can compare it to your brush if you are willing to fix the same issue on your brush too. And as you can see, there is some way of tuning the frequency on these brushes, and the main cause for not having vibration and all lights on, if there's no mechanical reason, is a mistuned brush, or a brush which has fallen back to its default state. And maybe this video might help you to recover your brush from the silent state. If you have any other problems with the brush, like mechanical problems or broken traces on the PCB, there is an interesting YouTube channel from a Lithuanian YouTuber, which I will link in the description box as well. He has lots of interesting videos about how to fix other main issues on these brushes, like as I said, the mechanical problems and the water damage problems. And he has also got videos how to open up the case here. So I will link that down in the description box. Check those videos out if you like. And yeah, thanks for watching so far. Good luck with your brush.